Hi YouTube, how's it going? It's Dan again, back with more videos on audio DSP. It's been a little while since I made one of these videos, but I've had an exciting year. In the last year I moved to Cincinnati, home of Skyline Chili and Bootsy Collins. I got a new job, and I finished grad school. In the last year there's been more positive response to these videos than I expected, so I figured I'd come back and make a few more of them. In this video we're going to go over reading in MIDI formatted notes and convert them into frequency and divisions of time in seconds so that we can actually play some music using the oscillators that we've made in the last few videos. I'm hoping that this video puts some of the other stuff into perspective that we've been learning so that you can see that the oscillators we've been making can be used to make actual music. In this video I'm going to use the song Autumn Leaves as an example that we can play with our oscillators. Autumn Leaves is a song from composer Joseph Kosma, written in 1945. It's a jazz standard. It's still played commonly today in many jazz circles. And it's a nice little melody that we can use to show this example. Before we talk about playing the notes, we first have to talk about the mathematics of how frequency gets interpreted from MIDI notes. The modern tuning system that's used by almost all Western music is called equal temperament. And what that means is one octave is divided equally into 12 semitones, or 12 notes. And that's how you get the 12 chromatic tone scale. Equal temperament means that the intervals are all just slightly out of tune by a few cents, but it means that we can play music in all 12 keys seamlessly without having to retune our instruments. Other tuning systems might have more perfectly tuned intervals, but they don't have this property of being able to play in all 12 keys easily, which is why it's used very commonly in modern music. This is the score for Autumn Leaves in standard notation. For those of you who don't read standard notation, what this tells us is where the notes are in time and what the notes are. So we can get the melody out of this as well as the chords. What we're going to do in this video is play the melody and the bass line so that we have two different examples of converting notes to frequency. When we're talking about converting from MIDI notes to frequency, we first have to understand that our perception of pitch is actually logarithmic in frequency. What that means is every time you double the frequency, it sounds one octave higher. The University of New South Wales has a great page that explains in detail the mathematics of this, but I'll summarize it here for you. This equation shows us how we can go from any MIDI note M to its corresponding frequency F. This equation shows us that the frequency of a MIDI note is related to 2 to the power of that MIDI note. That's where we get the idea that our frequency perception is logarithmic. The inverse of a logarithm is an exponent, so this is like the opposite of the logarithm. The divided by 12 part in the exponent shows us that we are dividing one octave into 12 semitones. The minus 69 part in the exponent shows us that we're offsetting this by the MIDI note 69. The 440 part of this equation shows us that we are assigning the MIDI note 69 to the frequency 440. The rest of the equation shows us the frequency for every other MIDI note besides 69. Check out the link in the description for the link to the New South Wales page. If we pull up octave, we can write a function that implements this equation so that we can get the frequency that corresponds to any MIDI note. Let's pull up octave. Resize the command window. We'll name our function MIDI to frequency. And we can use an inline function in order to implement this because it's very simple. So we can say at parenthesis m parenthesis. It shows us that our function named MIDI to frequency is going to take one argument that is called m. Say 440, which is our frequency offset for the MIDI note 69. Times 2 to the power dot caret for scalar power, m minus 69 quantity over 12 to divide one octave into 12 semitones, close parentheses, semicolon. So now if we run MIDI to frequency, say with 69, our answer is 440, which is correct, is the frequency of A440. Now we can try a different note. Maybe we want MIDI note 80. will tell us the frequency is 830.61. MIDI note 90, frequency is 1480, and so on. The other thing we have to talk about when we're generating music from our MIDI notes is to convert from musical timing into time in seconds. Fortunately, this is pretty simple, and we can use a few unit conversions in order to get us there. The tempo, or the speed, of most music is described in terms of beats per minute, or BPM. What that shows us is the number of quarter notes that happen in 1 full minute of that music. If you don't know what a quarter note is, it's sort of the steady, driving pulse between any song. If you think of house music, it's the kick drum that happens on every beat. That's a quarter note. When you think of the units in beats per minute, it shows us the number of beats that occur per every minute. We want to convert beats per minute into seconds per beat so that we know how many seconds every note in our score takes. In order to do this, we'll first want to flip beats per minute so that it's minutes per beat. We can do that just by dividing 1 divided by beats per minute. In order to convert minutes per beat into seconds per beat, we simply multiply by 60, since we know that there are 60 seconds in 1 minute. The units in this expression cancel out, and we get the number of seconds per beat. Let's write this equation in octave, as we did with MIDI to frequency before. First, we have to decide what BPM our song is at. Let's play Autumn Leaves at 130 BPM. So we'll make a variable called BPM and assign it the value 130. We'll also make a function called beats to seconds. Give it one argument, B, which will be the number of beats or quarter notes in our one note. And we'll do number of beats times 1 over beats per minute times 60. Remember, this is our conversion to minutes per beat. And this is our conversion to seconds per beat. Oh, sorry, forgot times there. So using this, we can figure out how long one quarter note is in seconds at this tempo. So it's 0.461 and so forth seconds at 130 BPM. And 2 quarter notes, or a half note, would be 0.923 seconds. Now that we know how to convert from MIDI notes to frequency and from beats at a given BPM to seconds, we're ready to play Autumn Leaves in octave. So here I have a script that plays just the melody part, and I'll start just by going through this. So at the top we have clear all, clears all the variables in our workspace. We have the constant BPM 130, which is our beats per minute, our tempo. I'm setting our sampling rate to 48 kilohertz, 48 times 10 to the third power. Our amplitude of our melody is 0.3, just to keep things a little bit quiet. And here I've gone through and programmed in the beats in quarter notes and the corresponding MIDI note of every note in our melody. So this is just the beginning part. Da, 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 da. You can see 1 quarter note, quarter note, quarter note, and then the equivalent of 5 quarter notes here in this melody, and so forth for the next part of the phrase. I've initialized an array here that will keep track of all of the samples in our melody, and then we have our 2 functions that we wrote to convert from MIDI to frequency, and then from beats to second. And then we have sort of the one-line function of what we did in the previous video, part 2, where we were generating oscillators using the linspace functions. So this implements one saw wave, tone at one frequency. We can give it the length that we want in seconds in L, and we can give it the period of the note, T, in seconds. So we'll make a loop here that goes through the index that corresponds to every note in melody beats. So it'll go from 1 up to the number of notes in melody beats. First, we'll get the frequency that corresponds to that note. Using our MIDI to frequency, we'll get melody notes at our current index. We'll get the duration that corresponds to that note, melody note duration. Using beats to seconds, we'll generate the tone using our saw tone, first by giving it the duration, and then giving it the period, which is just 1 over the frequency. This means the amount of time that one cycle takes in seconds. We'll multiply that by the amplitude that we've decided on, and we will append the current tone to the end of our melody. After this loop ends, we will have populated the melody array with all of the samples that we need in order to play this melody, and we will write it to the file leaves.wave at the sampling rate fs. So if we run this, change directory, pull up in Finder, and if we play our file, beautiful. Now this is great and all, but maybe we want to add a bass line to our melody for Autumn Leaves. So I'll pull up my other script. So this script is mostly the same. You can see that we've added an amplitude for the bass, the notes that correspond to the bass, and I'm using the MIDI note 0 here to correspond to silence in the initial part of the melody that picks up before the first chord. So to support this MIDI note 0, I've modified the MIDI to frequency function so that if the argument m is greater than 0, it'll multiply everything else by 1, and we'll get the same result. But if the MIDI note is equal to or less than 0, it will multiply this result by 0, and we'll get 0 frequency, or basically no note there. I want to play the bass line on a triangle wave. So if you'll remember from previous video, here is how we generate a triangle. Start at -1, go up to 1. From 1, go down to -1, and replicate that L over T times. This part is the same as before, just to generate the melody, and then we have something similar in order to generate the bass part. We'll get the frequency of this current bass note, get the duration of this bass note using MIDI to frequency and beats to seconds, and then we'll check and see if this note is 0. If it is, we'll just add in zeros to our tone. Otherwise, we will generate the triangle tone here by using the duration and the period, whenever the frequency, times our amplitude. And then we'll append this tone to the end of the bass array. We'll want to add the bass and melody arrays together, but Octave will be mad about that because they're different lengths. So in order to set them to be the same length, we'll go from the end of the bass array to the end of the melody array, those indices in the bass array, and assign them the value 0. So we'll just make the bass silent at the end of the melody. And we will overwrite our file leaves with the melody array plus every element in the bass in order to sum them together, and our sampling rate fs. So let's run this, and again pull this up in our File Explorer Finder. And there it is, we played Autumn Leaves. I do have to add in one caveat to the script though, and that is the fact that we are rounding the number of times that we are replicating each of our cycles of the oscillators. What this is going to do is mean that we can only play an integer number of times through our saw wave or our triangle wave, and that will get us probably off by plus or minus 1 cycle at the end of each of these. For something that's as short as our phrase from Autumn Leaves, it's going to be fine, but if you use the same script to play something much longer, eventually you'll end up out of sync with the actual timing. That said, this proves that we are able to play melodies with our oscillators that we've generated so far. The oscillators are still pretty basic and only give us a few different sounds, but it shows that they can indeed play melodies. In future videos, I'll go over strategies for generating more interesting oscillators and even oscillators that change over time. Other than that, give this video a like if you enjoyed it. Leave any comments if you have any questions or any comments to respond to. Other than that, I'll see you next time.